Okay, I have recorded. Actually, this is constant, but for the noise here, this is a random variable. So constant plus random variable becomes the y here is a random variable. This case kind of real world scenario in communication system. Okay, we specify our discussion today is a discrete time stochastic process. Remember last week that we already discussed about the discrete time. Yeah, discrete time means that we only sample in certain period. Yeah, we only sample in certain period, so we can name it as maybe T0, T1, T2, and T3 in terms of x-axis in time domain. So discrete time stochastic process is a sequence of random variable, typically denoted by xn. So this is the x0, meaning that this value has been taken in time 0, and x2 has been taken in time 2, in time 1, yeah, x2 taken in time 2, something like that, until maybe this is n. This is the random variable x taken in time n. Sometimes the problem that we can compute is kind of Carlton-Watson process. This is compute when and what probability a family name become extinction, yeah, become extinctions, yeah, disappear. Maybe if your family, you have a family name, and then usually if a man getting married with the woman, and then they have a children, then the children, then the family name of the children usually belong to the father in certain society. Yes, in certain society, but maybe in other society it depend on the mother family. It's depend on, but the point is when and what probability a family name become extinction after certain generations. It's kind of a certain case or problem. Okay, we move forward. Component of stochastic process here consists of the state space of stochastic process itself. It's kind of set of all value that the xn can take. So remember that this is a process, because a process, this belongs to the time domain. And you remember, let's say this is noise, for example. Noise is kind of stochastic process. Noise is fluctuated given the time periods, yeah. From this point, you remember that we have a minimum and maximum value. So this area become the set of value. the set of value of xn. Actually, in this range, this is the set all value of xn. Yeah, xn. Yeah. Okay, and let's move forward to the, for example, this is the discrete time. Discrete time we can notify as n equal to be 0, 1, or 2. Yeah, because of discrete, there is no 1.5. Yeah, no, there is no 1.5. In this case, the duration is space with 1 point. The difference is 1 and 1, 1, something like that. This kind of a discrete time. Okay. Anyway, and for the state is kind of a conditions representing the value, a certain value, a number of value that this is, let's say, phi dimensional factor S. This is state conditions. And in general, you can see here the state as mentioned that the state is a phi dimensional factor. So the number of state is equal to be phi. And there are m states. So we can write thing like this. The state is how to say, transitions. Yeah, the m state mean m combination. Yeah, m combination, because you can see here this is the bold s. Bold s consists of phi dimensional factor representing the value of the each element, and then combination of this, combination of 1 until phi can be defined as m state. So let's take an example here. Let's say S is consists of 0 and 1. 0 and 1. 0 and 1. So the S1 can be possible 0, 1, 0, 0, can be possible 1, 0, can be possible 0, 1, or can be possible 1, 1. So in this case, given the two-dimensional state, yeah, two-dimensional factor, so phi equal to 2, so it's kind of two-dimensional, and then we will have 4 state, right? For possible state. So the xn takes one of m values. So xn is member of this one, member of state space S. Any questions?
No, sir.
No. Okay. Okay. This is a gambler ruin. What is a gambler ruin here? Let's take a look. At time 0, I have x0 being $2, and each day I make a $1 bid. Actually, I don't want to teach you for being gambler, right? But yeah, this is just an example. If I win, the probability become winner is P, and the probability I lose with probability 1 minus P. Actually, it is simple. If you not win, so you win. If you win, and then the probability is P, and then if you not win, so the probability is 1 minus P. There is no other probability. There is no other possibility. Yeah. And then I will quit if I obtain $4 or if I lose all my money. Yeah, of course. If I don't have a money, I cannot make a game again. But after I think I have enough for having $4, something like that. So in this case, the state space means that the condition might be happen to me. In this case, 0, 1, 2, 3, and 4. This number represent the how many dollar I have. So 0 means that $0, 1 means that $1, and so on. Why how we can define these such conditions by this problem? Yeah, I think it is simple. Yeah, in the 0 condition, if I lose 2 times, right? 2 times or 2 days. Yeah, 2 sequential days I lose, and that I got $0. The condition 1, I only have $1. If maybe at the second day, in the second day, yeah, because in the first day I bid $1, so and then I lose, and then at the second day I have only $1, and then I make again. If I win, and then I got the $2, okay. So and so on and so on, and this process take place until 2 possibility at the end. Yeah, having $0 or having $4. Yes. Any questions?
I want to ask just for clarifying. So the gambler will each day will make a bet until his money reaches 0 or 4.
Yes.
Okay.
So the question is?
No. I just want to clarify.
Okay. Okay. One question to you. If I change this statement, obtain become 5. become 5. Define the state space. Define the state space. You can write on the chat box. Okay, you got it. Yes, thank you, Daniel, Jaffa. And then okay, let's modify. Let's modify the problem.
Sir?
Yes.
Sorry, can I ask a question?
Of course.
What is the meaning of xn equals to 4? Then xn plus 1 equals to xn plus 2 equals to 4. The orange part here.
Orange part.
Can you elaborate?
Oh, okay. Of course. Later, Ervigo.
Okay.
We still discuss this one. Okay. Yeah.
Okay, sir. I get it.
Okay. Wait a moment. Okay. I'm thinking about modifying the problem. Please try. For example, if I change this one become 2. So each day I can make a bid for $2. So please define this one. I mean the state of possible state here. Please write your answer in the chat box. The others is still, but I only change this one. The number of bit. Okay, anybody answer it? Okay, yeah, the answer is is correct. 0, 2, and 4. Any question, others? Yeah, for the others. Why 0, 2, 4? Any question? Any question? No? Clear at all?
It's clear, sir.
Okay. Okay, if clear, let's continue. Let's the xn is amount of money I have after the bid on day n. So, So x1 means that the amount of money I have after the bid on day 1. Okay. Okay. Okay, in day one, I write here, rewrite here x1. So in day one, there is only two possible conditions, right? The money I have, which is 3 or 1. 3, this condition that I win with probability P. And then this is the condition that I lose with probability 1 minus P. Okay? Yeah, something like that. So the condition is like this. Yeah. So, and then if xn equal to 4, if xn equal to 4, then xn plus 1 and then equal to xn plus 2 equal to xn equal to 4. In this case, after I win or I got $4, and then I quit, right? I quit. I terminated. I terminate for make a gambling. So in this case, we write that xn plus 1, I mean the day after I win. Let's say this is Friday. I got finally $4, and then the next day, because I quit, the next day and the day after tomorrow, xn plus 2, and so on, because I quit, my money is still 4, right? Still 4. That's the definitions. And in this case of xn equal to 0, it means also I quit because I don't have money anymore. Yeah. So in mathematically, we can write being x plus n equal to x n plus 2. Yeah. Tomorrow and the day after tomorrow also we still have $0. Okay, that's the point. Maybe it is clear, Figo, or somebody asking me?
Oh yeah, it's clear, sir.
Okay.
Yeah.
Okay. So move forward to the Markov chain definitions. The stochastic process Xn is called as a Markov chain if probability n plus 1 means that the condition after today is equal to G, some condition G, given certain or past condition, given past conditions. Yeah. So actually, yeah, from the previous example, the first day we have $2, and then if I lose in second day I have $1. If I win, I have $3. And then from this point, if I win and then I got $2, and if I lose, I get $0. In this case, if I win, I got $4, and if I lose, I get $2, and so on and so on. So the condition, let's say, let's say the probability being winner here, P, and then the probability getting loss is 1 minus P, right? And also this is P, and this is 1 minus P. This is P, this is 1 minus P. Yeah. The probability, the next condition equal to G, given the past condition is something, this is actually past condition. This is a future condition. So we can simplify in terms of writing. This is the second statement, the probability, the xn plus 1 means that the next condition, the future condition is G given current condition xn, yeah, n means that the day equal to I. Yeah. This is the transition probability. Transition probability. This process, you can see, is kind of chain, yeah, this kind of chain. And you can see here, I make a circle using a blue color here. Sometime, if we have $2 in certain step, we back on $2 with certain probability. Yeah, you can see here, actually, after 2 become 2 again, the probability is simply write 1p multiplied by p. It's kind of chain. It's kind of chain. This is kind of Markov chain. And the characteristic of Markov chain, you can read here, the future behavior of the system depends only on the current state E and not on the previous state. So the next condition is only depend on the past state, yeah, on the current state. There is no logic that the current condition is depend on the current condition. No. In this Markov chain definition, the logic is the next condition is depend on the current condition. Any question? Any question? No? No question. Okay. Oh, oh. Okay. And then we move forward to stationary transition probability. If from the meaning stationary transition probability, if the probability from, yeah, you can see xn plus 1 equal to g given, or the previous state xn equal to e, it is equal to the probability x1 equal to g, and then the next is equal to e for any time, yeah, for any n means that for any time they don't change over time. And then we will only consider stationary Markov chains. In this case, we only consider as stationary Markov chains. And given the number of states, then we can make one-step transition metric. Yeah, actually, one-step transition metric is a metric. Yeah, metric consists of state transition, because the transition given in probabilities, so the every element is probability. Probability representing the changings one state to another state. So you can see here, this is P, big P. The big P consists of 3 by 3 matrix. Why 3 by 3 matrix? It is simple, derived from the number of state here. We have 3 state, 0, 1, and 2. So any how to say, any possibility for changing this state, so we can put into the matrix. For example, the P00 means that the transition metric representing the probability condition 0 and then becomes 0 again. 0 and 0 again. Is it possible, sir? Oh, of course. It is possible in many scenarios. For example, maybe the average temperature today might be 32, right? 32. And then tomorrow, after we observe, also 32. So the state is same, right? The state is same, is 32 degree of Celsius, so it's mean that the value, the state is doesn't change from today until tomorrow. But if we have another possibility, let's say become 33, so this is a kind of changing temperature, yeah. And even if we have a same state, same value, 32 and 32, there is a probability could exist. So we can say like maybe the probability that the tomorrow is equal temperature with today, maybe with the probability, maybe we can say 90%. Well, 90%. So there exists a probability, right? Something like that. Okay. And so on and so on. Let's say the P01 means that the probability, the changing state from 0 become 1, and so on and so on. So because we have 3 states, that's why we have a 3 by 3 matrix. Okay, any questions? And for each element, you can see here that PIG equal to the probability representing that the previous condition is E and the next condition is G. Something like that. Okay, any questions? Seem no question. Oh,
No question.
Oh, no question. Okay. Okay. Okay, bro. The properties of transition matrix, properties of transition matrix you can see here. Actually, we can easily directly to the table. The properties simply say that in row element, the total probability should be equal 1. This is the total, it should be 1. This is total should be 1. This total should be 1. This total should be 1. And this total should be 1. Yeah. The first properties. The second properties, each element here, let's say this one, this one, this one, yeah, this one or this one, yeah, this one or this one, yeah, it should be greater than or equal to 0. Means that there is no allow to or being negative. No negative value here because of the probability. There is no negative probability. Okay, that's the point. Here, the total should be 1, yeah. And for each element should be equal or greater than 0. Yeah, yeah. Any questions? No? Haha. Okay, this is one exercise you can read. Okay. This is a case for transition matrix, yeah. Special case for Markov chains. Let's say two aging computers are used for word processing. Then, when both are working in the morning, there is 30% chance that one will fail by evening, and 10% chance both will fail. So there is two computer, and then both are working in the morning, and then there is 30% chance one will fail. One will fail, so the rest of computer that's still good, yeah, still okay, one, right? In this case, the probability is 30%, right? 30%. In this, and then both fail. So the current good condition there is no, but we have 10%, right? Something like that. If only one computer is working at the beginning of the day, there is 20% chance that it will fail by the close of business. And okay, in case of only one computer working and the next day, so we started in here. So fail, so we will have no computer again. This fail is 20%. If no fail, so we still have one. So in this case is 80%, right? If neither is working in the morning, the office send all work to a typing service, yeah. Okay, in this case, the office send all works to typing service, kelayanan pengetikan, ya. Oh, sorry, bahasa Indonesia. Computers that fails during the day are picked up the following morning, yeah, repair and then return the next morning. And the system is observed after the repair computer has been returned and before any new failure occurs. Okay. Any question from this example? Which part that you still confused? Okay, let's move forward. Let's summary for this problem or this case. Index 0, state 0, this kind of different perspective, yeah. No computer have failed. No computer have failed. The office start the day with both computer function properly. And the index 1 means that the state 1 computer has failed. One computer has failed. The office start the day with one working computer and the others in the shop until the next morning. Index 2, both computer have failed. All work must be sent for the day. Yeah, so all the work should be sent to the typing service. Okay. This is the event and probabilities for computer repair. Yeah. Index 1, current state 0. Sorry, I mean index 0, the current state 0. Neither computer fail, the event, and the probability is 0.6, right? 0.6, because you remember that if computer fail in the evening is 30%, if both fail in the evening is 10%. So no computer fail, 1 minus 3 minus 1. So the rest is 0.6. And 0.6, if in the evening there is no computer fail, means that the next day is going back to this condition. Going back is to the index 0. Index 0 means that the next day is still, the computer is still okay. So this one. Yeah. And then one computer fail means that at the evening only one computer that works, means the next day follow the second state, I mean the first index, yeah, first index here. First index defining that remaining computer does not fail and other is returned, or remaining computer fail and other is returns. Yeah, means that there is a still computer in the office, and then if in the evening both computer fail with the probability 0.1 or 10%, so the next day will be at the state index 2. Yeah, index 2, the current means that both computer are returned. Yeah, are returned, or return means that there is no computer in the office. Yeah, something like that. So move forward to the index 1. Index 1 representing that only one computer exists in office. So the event could be remaining computer does not fail and the other is returned. Remaining computer fails and the other is returned. Yeah. This probability is 0.8 and the other is 0.2. If 0.8 means the return, so the next day is okay, the computer works well, so back to the index 0. But if still computer fail and one returns, yeah, means that the one computer is okay next day. So is the next day the state is index 1. The last for index 2 defining that the computer are returned means that today we don't have a computer but a returns. So the probability is 1. Probability is 1 means the computer returned today, but we don't have we no works today. The computer just returned. Okay. So the next day, I mean tomorrow, tomorrow we'll back to the state index 0, means that the computer works well for both. Okay, any questions?
No question, sir.
Okay. Okay, let's move forward again. We already discussed about the state transition matrix. So plus network. So today plus network. In the slide is plus network. Network is kind of connection, yeah. Connection between point to point, point to multi-point. So in this case, once we have matrix, the transition matrix, and then we can make a chain. We can make networks. Kind of this one, yeah. You remember that the state is 3, S is equal to either 0, 1, or 2, right? So in this case, we will have 3 points, 0, 1, and 2. Okay. Okay. And then actually, what is the circle arrow here? Circle arrow representing that the current state will be equal to the next state with probability 0.6. Okay. And this current state 0, the next state become 1 with probability 0.3. If the next state become 2, the probability is 0.1. And you can see the outline, I mean the line out, out from this point, we have 3. 1, 2, and 3. Means that the next condition would be same with current condition, so 0 to 0, or 0 to 1, or 0 to 2. Yeah. Okay. For the second condition, I mean the first condition first, condition 1. Condition 1, the possibility changing is the next being 1 or being 0. Being 1 if the current condition is 1, and the next condition either 1 or 0. You can see here, the next condition is 1, 1, 1 being 1, and 1 being 0 here, with the probability 0.2, 0.8, right? Okay. For the others, 2, condition 2, only one change here becomes 0. There is no self circle. So the only possibility is being 0. Yeah. The next must be 0. next condition must be 0. So because the next condition must be 0, so the probability is 1. It means that the next day must be 0. The probability is 1. It's very, very certain. Yeah. This is how to transform from the transition metric to the network, or that we can call as Markov chain. Markov chain. Yeah, because it's kind of chain linking to from one point to another point. Any question?
Not yet, sir.
Not yet. Okay.
Yes.
Everybody can see, yeah? Please exercise by yourself. Please conduct the exercise. I have a transition matrix here and draw the transition network. Draw the transition network for this condition, this transition matrix. Okay. Anybody, please show me for your answer. You can write by yourself in a white paper, and then you can, how to say, in white paper or in computer, it is okay. Maybe make a circle handwriting, and then upload it to the chat box. Or you can write in this screen as well, if necessary. I will give you access. Yeah.
Sir,
Yes.
I already draw in a paper. Should
Okay,
I show
okay.
you by video or I send it in the chat box?
Send it to the chat box. Yeah.
Okay.
Yeah.
I already sent in the chat box, sir.
Okay, okay. Thank you. How about the others? Two one is actually 20 2.7 3 minus 1 0 1. Okay. How about the others? Okay, there is. Okay. Okay, nice. Okay, Daniel.
I think I got one wrong, sir, from 0 to 2. For my drawing, I think it should be 0.1, not 0.2.
Okay.
Yes, that's the part where I'm wrong.
Hmm. So, okay, thank you very much for your participations. Oh no, why I remove this figure? Yeah, actually, if I don't mistake, it should be 1, it should be 1, it should be 0.2, right? So in this case, we make the network. This is a 0, this is 1, this is 2, right? This is 2, and then actually for the first row is quite similar. So it's kind of like this, 0 0.9, 0.6, and means that 0 to 1, 0 to 1. So here something like this is 0.3, right? Yes. And this is for 0 to 2 is 1.1. Yes, it is correct. And then for the second line here, second line means that this 1, yeah, for 1 to 0, yeah, 1 to 0, 1 to 0 is something like this, 0.8, and this is 1 to 1, 1 to 1 means like this, 0.2, and then 0, 0 means that there is no network from 1 to 2, there is no network, yeah. And the third row means that here is 2 0, yeah, 2 0. So we write here 2 0 here, 0.7. Okay, and this is a 2 1 2 1 is being like this, is 0.1. Okay, and 2 2 and 2 2 2 2, yeah, and 0.2, yeah, that's the answer. Okay. This is for your exercise at home. Please do it by yourself. If I have a network like this, 0, and this is 1, and this is 2, and this is a 3. Okay. Okay, and this one is 0.5. This one is 0.4. This one is 0.1. Then for the second is something like this, 0.7, 0.3, and this one 0.2, 0.2, 0.2, 0.4. And this one 0.3, this one 0.4, zero point 3. Okay, this is exercise for everybody. Please conduct by yourself and submit to the MAS. The task is please make transition metric. Yeah. Please make transitions matrix from this network. Yeah, from this network. Yes. Okay, that's all. Yeah. Okay. Don't worry, I will upload it to this video. Yeah. Clear all. Yes. Okay. Let's move forward. So this is just explanation of transform from the state to the whether the transition metric or transition diagram. Yeah. First, specify the times when the system is to be observed, of course. Define the state factor, how many states you have, list all the state, and number the state, give the number, yeah. For each state is, at the time n, identify all possible next state s that might occur when the system is observed at time n plus 1. Okay. Determine the state transition matrix P. Of course, this is simply this transition matrix is a square matrix phi by phi. Yes, draw the transition diagram. Yeah, you just exercise by yourself. I think there will be no problem for you. Okay. Any questions? No. This is the another example. Yeah. You can exercise by yourself as well. Yeah. This is the state definition for today's requirement. As the number of state growing up, so you have to be carefully defined. Yeah, carefully defined. Yeah. The second, and then you have to define the number of state possible. Yeah, possible state. Yeah, something like that. So in this case, we have 5 states, 0 until 4. Yeah. So in this case, we can simply from this matrix is 5 by 5. Yeah, 5 by 5. Yes. Yes. And yeah, you have to be carefully placed for the element number. Yeah, number of element. Number of element. How much the probability should be written here. Okay. This is another example. Brand switching example. The number of consumers switching from brand I in weeks 26 to brand G in weeks 27. This called is contingency table used to construct transition probability. Yeah, it's kind of market study here, kind of how to study, analyze the customer behavior changing its brand, maybe because of advertisement or because of endorsement, something like that. So thank you for the participation here. Still, Muhammad Rehan just uploaded for the answer. Thank you. Okay. Okay. This is Markov analysis, means that the kind of information that we can come up from the computation of using Markov chain. For example, in this case, the state variable explained is equal to brand purchase in weeks n. Action represent a discrete state as discrete time stochastic process, whereas we have 3 states and number of sequence time. If X has a Markovian property, P is stationary, then Markov chain should be reasonable representation of aggregate consumer brand switching behavior. So in this case is to know to study the customer behavior. Yeah, the potential study predict market share at specific future point in times, assess rates of change in market share over time, predicts market share equilibrium if there exists, and evaluate the process for introducing new products, something like that. Yeah. Any questions? No questions? Once the state become more complex, yeah, this kind of a process that convert to the Markov chain. Sometimes a non-Markovian stochastic process can be transformed into Markov chain by expanding state space. Yeah, expanding state space means that putting any possible conditions. Yeah. Example, suppose that the chance of rain tomorrow depends on the weather condition for previous 2 days, yesterday and today. Specifically, the probability rain tomorrow become rain, rain last 2 days, yeah, the probability and become rain for last 2 days, yeah, last 2 days is already rain, and the probability is 0.7, and rain tomorrow if the probability rain today but not yesterday, 0.5, and then rain yesterday but not today, not today, 0.4. No rain in the last 2 days. No rain in the last 2 days. You can see here 0.2. So the question is, does the Markovian property holds? Means that this condition follow the Markov properties. Does these conditions, these problems follow the Markovian properties or not? You can simply see that, you can see, if you sum up together, the total is less than 1. Less than 1. The total probability, it is impossible to be less than 1. So, how about the solutions? We put another way. You can see here how to model this problem as Markov process. The state space, this is the given state space. 0 means that 2 days before rain. 1 means that today is rain, but sorry, the day before yesterday is rain. Today is rain, but yesterday no rain. Today and yesterday no rain. Yeah. So in this case, the transition metric we see here. First, we put the row parameter and column parameter, and for the row parameter. The column and row parameter is really equal. You can see here the probability today and tomorrow rain. Today no rain, but sorry. Today and yesterday rain. Today and today no rain, but yesterday rain. Today rain, but yesterday no. Today and yesterday no rain. Yeah, you can see here. Given the problem here that the next condition means that the today and tomorrow rain, and next is rain. So here is 0, but if the today rain and tomorrow yesterday rain and tomorrow rain become 0.7. Okay, and then given today rain, yeah, the next day is today no rain, but next day is rain. You can see here 0.3. Actually 0.3 is simply by 1 subtract by 0.7. Yes, and from this case is of course 0. And so on and so on. Any questions? Any questions? No? Are you there? And the next topic is multi-step transition, means that we have multi-matrix, yeah. So in this case, we have not only one matrix, but there is a step matrix. The step matrix is depend on the problem, will be equal or not. How do we calculate the probabilities for transition involving more than one step? Consider ERS auditing example. For example, this is state 0, no audit, and 1 is audit. The transition matrix given like this. No audit and no audit is 0.6. No audit become audit, become 0.4. Audit no audit to no audit 0.5. Audit to audit 0.5. Okay. And then let the probability going from I to J into transitions. To transition simply mathematically just a multiplication of two matrix. Yeah. If two transitions mean that multiplication two matrix. So the result is this. The resultant matrix indicates, for example, that the probability of no audit 2 years from now, given that the current years there was no audit, is, you can see here, probability become from no audit to no audit in 2 years is 0.56, decreasing, yeah, actually decreasing, yeah, decreasing. And audit to be non-audit to be audit, increasing, and no audit to be audit. This is audit to be no audit, increasing, and audit to be audit, decreasing. This is application of multi-transition. Yeah, multi-transition. In this case, we can predict. Yeah, we can predict how many in the future, what kind of behavior in certain application, how much the probability in some cases changing from current condition to the next current condition in certain period of time. Okay, any questions?
No, sir.
No,
It's
okay.
good.
Okay, let's move on to n-step transition probabilities. Yeah, you can see here. It is nothing. I mean, this mathematics is nothing because the important, actually, this expression is derived from the multiplication in the matrix. Yeah, if you remember that the multiplication on the matrix, yeah, this is what we call as a Chapman-Kolmogorov equations. For each IG entry, meaning that the IG element, yeah, IG element can be computed part by part is using this expression. If you understand the what? The multiplication, matrix multiplication, no need to be confused about the Chapman-Kolmogorov equations, because this is really representing the multiplication matrix multiplication for each element. If you don't believe, you can check by yourself. If you remember that, sorry, the composing the element consists of multiplication each element in matrix and then sum up together, right? So that's why this is a multiplications and this is a summation symbol. Yes, Okay. This is another sample of state transition network. Given this network, actually, I hope you don't have a problem for transforming from this network to this transition metric here. You can simply see here how many states we have. Oh, 5. Total is 5. 0, 2, 0, 1, 2, 3, 4. So we can simply think that the matrix will be 5 by 5. Okay. And then we fill up for each probability. Yes. And then finish for making the state transition metric. Yeah. And then this is a very special case in terms exists a very small non-unique number, which is the probability not really exact. There is some error. Any possible condition, any possible state, the next state that exists. For example, here, eta is very small non-unique number. Yeah, this is a very small. But actually, you can see here, this is the total is 1, right? So it should be 1 point something. Yeah, this is the error. 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 This is the error. Because of error, the meaning of the matrix is steady state probability doesn't exist. Okay, something like that. This kind of computing the transition matrix in certain application using Excel, yeah, it's okay. Okay, this is the steps. This is in case of brand switching example. You can reread from previous problem and then convert to this matrix as well. This is nothing. The transition probability for n step means that we have to multiply the matrix. Yeah, we have to multiply matrix with n multiplications. So in this case, if we have n step means that we have n powered by p powered by n. So it is equal to the matrix p multiply by matrix p. So this is 1. Maybe let's say this is 1 until matrix p here. N. Let's say this is 1, this is 2, this is n. So this multiplication becomes p powered by n. Yeah. This case for n step. Okay. Steady state probability, you already know that steady state probability, this should be equal to 1. Yeah, if there is equal or not equal 1, so it's not stable conditions. Means that there is an error. If the total is less than 1, less one. So there is another possible condition that's still unknown, something like that. Because of unknown, there is no stable, no steady state. Still unconfirmed what kind of condition will be have. So in this steady state condition, otherwise the steady state condition means that the total should be already well defined, means that the probability of rho is equal to be 1, something like that. Okay. Okay, this is for brand switching, application for brand switching derived from the problem axis here previously. And yeah, the steady state prediction are never achieved if there is error. And then change P over time means that the composition, each element change over time, the probabilities change over time. So it is not steady state anymore. Okay. Change in the nature of dependence relationship among the state. It's also change in the nature of dependence relations among the state. Means that the change, the value here is depend on the probability. The change in the nature of dependence relationship among the state. So it means that another view that the value of each element, the value probability of each element depend on the probability of another element. Depend on the probability, not depend on the condition. Yeah, not only depend on the conditions. That's, we cannot say that it's steady state predictions. Yeah, this steady state prediction or the steady state matrix is kind of a diagnostic tool for decision maker, of course. And steady state probabilities might not exist unless the Markov chain is ergodic. Ergodics mean that, yeah, ergodics mean we should define that each element doesn't change. If change, we cannot say it is a steady state network or steady state matrix. Any questions? No questions. You can see here is total is 1. The meaning of ergodic is kind of the value that has been taken in certain period. This value, the state value, doesn't change. This means the ergodic. In terms of Markov chain, if it is aperiodic and allow the attainment of any future state from any initial state after one or more transitions. If this condition holds, that the phi equal to the limit of n become infinity, yeah, and then the p doesn't change, means that p means a constant, and the limit n means that the changing over time, yeah, the duration of the discrete time, how many transitions, yeah, transitions. So how many steps here, here you can see this is the element limit the probability powered by n should be constant, you see, should be constant. When n, yeah, taken in very unlimited number, and the result of probability is constant. The result of probability is constant. This kind of ergodic constant number after taking from many experiment, many observations, something like that. Okay, this is kind of game, yeah, you can read by yourself. Yeah, maybe summary of this material today: how to define the state discrete time process, how to construct the state transition matrix, how to find the n-step state transition probability using Excel add-in, how to determine the unconditional probability after n step, and how to determine the steady state probabilities using Excel add-in. Yeah, no need to use using Excel add-in. Using you can exercise by yourself, but the thing that you have to point out that steady state probabilities, there is no error, and the total probability for the row, the row matrix, it should be 1. Yes, that's all the material for today. Then I will upload this material, and don't forget to submit your assignment before the deadline. The deadline will be announced at the mass. Thank you very much. Any questions? Yes, no change. No change. Because a bit back to this one. I remove this one. This one, you can see this is pi. This pi is constant, representing the constant. This constant can be achieved when the n going unlimited. Yeah, means that this is unlimited, multiple steps. Yeah, multiple step, and the multiple step will limit to the some number. Yeah, some number, constant number. Result of the multiplications. Result of the multiplication of many matrix. Something like that. Okay, any questions? Any questions? No? Regarding to the final examinations, so from material from the midterm examinations, we never been evaluated. I mean, I never evaluated since the hypothesis testing and random estimations. I consider for having quiz before the final examinations. Maybe next week, but yeah, I understand that next week maybe is holiday, so I will give you some period time for taking the quiz. So what is your opinion if I give you one quiz before final exercise? Any comment? Any comment? So everybody agree?
I personally agree, sir.
Agree, yeah? Okay. So, yeah, actually, if you take the quiz, I consider to split the material for the final exercise, final examination. I consider the quiz material only for random estimator and hypothesis testing, and then this is the material for the quiz. After that, the material for final examination is from random estimator, parameter estimator until today. So it's kind of more lighter for the final examination. So I mean for the studying, the material is more easy, maybe, more easier. I mean less complex. I mean, for the detail I will explain at a mass, so please monitor the mass, something like that. Any questions? Any question? No?
Sir?
Yeah.
Since this is our last meeting, we would like to show something to you as our appreciation for your kindness and your knowledge the past semester. So yeah, thank you very much, Dr. Ajib Setio Arifin, as have become our very remarkable lecturer for this semester.
Oh, really?
Yes, sir.
Why? I'm really surprised. Okay, wait a moment. I will take a picture. Okay.
Yes, sir.
It's a very memorable time.
I really didn't think the pen, but it's okay, I guess.
Okay. Okay. Oh, that's nice. Okay. Okay. Cool. Okay. Thank you very much. Appreciate.
Thank you very much, sir.
Thank you. Appreciate.
Thank you too, sir.
Thank you very much, sir, for everything you've
very
done.
much, sir.
Okay. See you.
Thank you, sir.
Yeah. See you next.
Thank you, sir.
Next 2 weeks.
Yes, sir.
Okay, sir,
Thank you,
yeah.
Okay.